In this video, we're going to look at the ML2 method of selecting a prior distribution. But before doing so, let's just briefly review likelihood functions and the maximum likelihood estimator. Now this notation will maybe not match exactly the way we use it in the textbook, but we just want to get the basic idea. So let's suppose that we have a random sample with a common distribution that depends on our parameter theta, and that common density, or PMF, is what we see here. Now the distribution of the vector of the entire random sample, if you will, would just be the product of those common PDFs or PMFs as we see here. But when we look at things in terms of likelihood, rather than regarding the x's as the variables and the theta as given, we're going to flip that around. We're going to regard the x's as given and the theta as variable. And when we do that, we refer to this as the likelihood function. And the idea is that it gives us some idea about how likely is it that we would have observed the data we did given a fixed value of theta. So let me just go through the idea here. So again, suppose we have some data given, that's represented by the black dots. And so suppose that we know that this comes from a normal family. And let's just, for simplicity's sake, suppose that we know the variance of this normal distribution, and the only unknown is the mean. So we just don't know where the center is. So I think it's pretty obvious, if we consider those three curves that are drawn there, that the best curve that fits that data is the orange curve. And that's the idea of the maximum likelihood estimator. If we suppose for a moment that the orange curve is the actual distribution, the actual density, then these likelihood function values would look something like this. Okay, so that's one possibility. Let's suppose that on the contrary, it's the green curve. Then those likelihood values would be looking like this. And that's not too convincing. And then we could do the same thing with the red curve. So then the question is, how do we quantitatively identify the orange as the best? Well, we simply multiply all of those likelihood values together based on the curve that we're considering. And then we choose the value of mu, the center, so that product, that likelihood function, is maximized. And therein lies the source of the name of the method, maximum likelihood estimator. Okay. All right, so recall that if we take the conditional distribution of x given theta and we multiply it by our prior distribution, that gives us the joint distribution, which in this book we typically denote as h sub x theta, right? That's what the integrand is here. And then if we integrate that joint distribution over the entire parameter space, if we integrate out theta, then what that leaves us with is the marginal distribution for x, and that's what's boxed in green there. The thing to focus on here is the fact that whatever we get depends on the prior that we used, obviously. And so if we pick a bad prior, then we're going to get a bad marginal. And you can see that in the textbook here. If we treat f as definitely known, then the marginal, as it says there, reflects the plausibility of the prior, pi. And so for any particular observed data, we would hope that the marginal would be big. So if we wanted to compare those two priors just in terms of one observed data value, then we would pick the prior which maximizes the marginal for that particular x value. If we have this inequality, then that provides more support for pi 1 as being a good prior distribution as opposed to pi 2. And so we're going to, as the text mentions there, it's reasonable to consider this as a likelihood function for the priors. And then what we want to do is maximize over our class of priors. So we're going to have some class, which we're going to call capital lambda. And what we want is to choose the prior distribution so that the marginal of x according to that prior distribution is maximized over the entire class of prior distribution. And whatever that is, that's called the ML2 prior. Let us look at an example. So let's suppose that our xi given theta I follows a normal distribution with mean theta I and known variance sigma sub f squared. For I equals 1, 2, and then all the way up to little p. And then so our parameter here is a vector parameter, as we see here. Furthermore, suppose that the theta I are IID with common distribution normal, as we see here, with mean mu sub pi and variance sigma sub pi squared. And both of these parameters are unknown. Now notice from here, if we go back to our xi given theta I, notice that the xi's in this situation do not comprise a random sample because the theta i's can be different. They all come from a common distribution, but we're not guaranteed, and in fact, most likely, I can't imagine that they would ever all be the same. So this means that we're going to have to look at a class of priors for the parameter vector here. And because the theta i's, though random, are IID, then we know that the distribution of the parameter vector is just the product of the distributions of the individual components, and each individual component, as we mentioned earlier, follows this normal distribution with these two unknown parameters, or we can say according to this hyperparameter, which would be the vector consisting of those two. And those again are what we need to choose. In fact, they serve as an index to our class of prior distributions. And so we want to choose these parameters using the ML2 method. So recall earlier that in this situation we noted that the marginal distribution of the xi is what we see here. So we want to choose the ML2 prior, that is, we want to select the right mu sub pi and the right sigma sub pi so that we maximize the quote-unquote likelihood function according to the distribution, the prior distribution class that we have. So let's first look at the marginal distribution for our random vector x, which is given here. And again, we're taking advantage of independence here. And so each xi is distributed like we see here. We noted that earlier. That's the marginal distribution. And so if we do a little bit of algebra, we get this. And the ML2 prior, according to the formula, is the prior, our pi hat, if you will, is the prior distribution which will maximize the marginal distribution at our data. So just as with any likelihood function, we treat the data as given, and we treat the parameters that determine our prior, in this case, as variable. And so we want to treat the mu sub pi and the sigma sub pi as the variable. So to that end, we're going to do like we normally do with this likelihood business, and we're going to look at the log likelihood. because that's easier to work with, and it preserves maximums and minimums because of the fact that the log function increases. So the log likelihood is what we see here. So we essentially have a constant. I think that constant in this case would be negative p over 2 times the log of 2 pi, but whatever, we're going to take the derivative and the constant's going to go away. And then minus p over 2 times this, and then minus this part here. And notice that the last term does not have a log on it because before it was the power on the exponential. And so typically the log likelihood is denoted with a little l, and so that's what I've done here. And so now we want to take the derivative of the log likelihood and proceed to figure out what values of mu sub pi and sigma sub pi maximize the log likelihood. The partial derivative of the log likelihood with respect to mu sub pi is equal to what we have here, because notice that in this first expression mu sub pi is not involved, so the only place we really have mu sub pi is here. So that part's just basic calculus. And so if we set that equal to 0, then we get this equation here, and then that implies that mu sub pi is equal to x bar. And that makes perfect sense. So, and then because of the form of the marginal, then it is clear that the maximum occurs at x bar. To say more about that, let's focus on this part here. And this sum of the squares is going to be minimized whenever mu pi is equal to x bar. And since this is a negative in front, since we have a negative in front, this expression here would be maximized at x bar. And then so would e to that power and so forth. Hopefully that convinces you that we really do have the right answer here for the first part as x bar. Now we've got to tackle sigma sub pi squared. So in order to do that, let's replace mu sub pi by x bar everywhere that we see it. And then from there, we will focus on maximizing this expression where now we just have one variable, which is sigma sub pi squared. And so then we'll take the derivative with respect to, we're going to take the derivative with respect to sigma sub pi squared. The derivative of this part will just be negative p over 2 times 1 over this part here, times the derivative of this, but with respect to sigma sub pi squared, which is just 1. So that hopefully explains this first term here. For the second term, it's similar to the fact that the derivative of 1 over x is negative 1 over x squared, right, if x is a variable. So that derivative gives this. And then, of course, like we always do, set that equal to 0 and solve. And what we get is what we see here. And then we need to verify that we actually do have a maximum there. So the way I chose to do that is, notice first we made I made a replacement here using this fact here that the variance is what we see here. And so then this sum here is just p times s squared. Oh, and then from there we see that this derivative will be positive if and only if this numerator is positive, right, since the denominator is clearly positive. And so that's if and only if sigma sub pi squared is less than s squared minus sigma sub f squared. I skipped a few steps there, but I'll let y'all do the math there. And then we finally see that what is equivalent to this condition, that derivative is positive, is this, and then what's equivalent to that derivative being negative is what we have here. So that tells us that this log likelihood function increases as our sigma sub pi squared increases up to this value here, and then after that it decreases. So we do have a maximum at that critical point. But now there is one detail that we need to take care of, and that is that, you know, this quantity on the right could be negative. So we want to make sure that we choose the maximum of 0 and that critical point there. And so our ML2 prior turns out to be the normal distribution with these two parameters here, where mu sub pi hat is x bar and sigma sub pi squared hat is the maximum of these two numbers here.